Now I want to show all of these properties in an explicit example, which is called infinite square well. Now we reduce the Schrödinger equation to time-independent form. Let me write it in a little bit. And all we need to do is, like, given the external potential, solve, find wave functions, and try to understand properties. And infinite square well is the simplest possible external potential, V of x. It's given by 0 if x is inside some domain, 0 to a, and infinite otherwise. Let me sketch the potential for you. So this is x is equal to 0. This is x is equal to a. This is v of x. Here, in the dashed region, v is equal to infinity. Here, v is equal to infinity. And here, v is equal to 0. Now we can immediately ask, what is the probability to find a particle here in an infinite potential? What is the probability? 0, right? Because it's infinite, it cannot be there. It can also not be there. It can also not be there. So basically, because of infinite potential here and here, particles should not exist. There is 0 probability the particle can ever go there. And from there, we can immediately conclude psi of x should be 0 outside the box, because v is infinity there. And inside, v is equal to 0, then our task is to solve this equation. And maybe here's a little exercise for you if you want to test your understanding. So exercise. Based on general Schrödinger equation, like think about a Schrödinger equation in an arbitrary potential. Show E needs to be bigger than V minimum for any normalizable solution. So no calculation needed. You just need to sit down and think about derivatives and like slopes and things like that. But the conclusion is, because we are interested in normalizable solutions, E needs to be bigger than minimum of V. Wherever minimum could be, your energy should be bigger than, equal or bigger than that minimum. Okay, and that means here this E has to be bigger than 0 in our case. Actually, it could also be 0, but that would be a null solution, and there's no point of thinking about such a solution. So in the following, I'll assume E is bigger than 0 and try to find solutions for that. So let's rewrite the equation. This is b squared psi dx squared is equal to minus, I carry this minus to here. So this is 2m divided by h bar squared. So this is E and this is psi. So our job is to solve this equation. And now on the right hand side, m is a mass, positive quantity, h bar is a constant which is positive, and we also just argued E is positive. So this entire thing is a positive constant. So let's define it to be k squared, which is standard practice. And how do we solve differential equations? I think you may have like a better answer than I do. For me, you know the solution and you substitute. And if you have a better way, good for you. But I'll do it like this. Things like this, I know how to solve. This is like either sine kx or cosine kx. I try, and if it doesn't work, I try other things I know, and there are already finite number of functions, one or the other works. If it doesn't work, I put it in Mathematica, and Mathematica gives me a result. I took it and I continue from there. So for this one, let's take the derivative, dx. Derivative of sine is cosine, this is k times cosine kx. And one more derivative, dx. Derivative of cosine is minus sine. And there's one more k squared. And this is sine kx. And that's exactly the equation, right? Second derivative is equal to minus some k squared times psi. And the same thing here. So if you take the second derivative, you are going to find this is minus k squared cosine kx. And sine kx is a solution, and cosine kx is a solution. And by linearity, the most general solution psi of x is going to be given by a times sine kx plus b times cosine kx. Good? Any objections? But a, b, and k are at the moment arbitrary constants, and I need to determine what they are. And I can use the information I just started with. We said psi needs to vanish here and here, right? Let's use these conditions. So, at x is equal to 0, psi should be 0. That's a requirement. And if I put 0 there, a sine 0 plus b cosine 0. Sine 0 is 0. This term is gone, 0. And we require this to be 0. Cosine 0 is 1. The only way this can be 0 is if b is equal to 0. So we eliminated 1. The second one is x is equal to a. Again, psi should be 0 there. Now b is gone, so I'm not writing it anymore. A sine k times a should be 0. And something times something else is 0. Either this one should be 0 or this one should be 0. But if a is 0, it's like a 0 solution. There's nothing to talk about. So you better have the second one, so the sine term to be 0. But for this to be 0, k times a should be equal to something times pi. Actually, okay, let me be a little bit pedantic because the textbook is doing it too. So it can be 0 plus or minus pi plus or minus 2 pi plus or minus n pi. First, Sine 0 is 0, and that's like a null solution, so I'm not interested in that. So I get rid of that. And sine x is equal to minus sine minus x. So for each minus, I can take it outside. And because, I'm interested in linearly independent solutions, I can also forget about that. At the end, I need to have n times pi as the valid solutions where n is equal to 1, 2, 3, dot, dot, dot. Good? This gives me k is equal to n pi over a. But how did we define k? K was defined here. This one. K is square of this. Square of k is this. So this one was equal to k squared. Now I determined k squared. Let's do this. N squared pi squared over a squared is equal to 2m over h bar squared e, and this gives me e is equal to h bar squared over 2m pi squared over a squared and n squared. Okay. Sometimes to emphasize the n dependence, because there are like discrete set of solutions, we put subscript n there. Good. Basically, we are saying only discrete energies are allowed. No other energy is possible in the box. Good. And lastly, I used boundaries, I used the solution, and last thing I need to do is normalization. And what I need to do is like integrate from 0 to a dx psi n of x, and my psi n's are given here. Let me write them here. So psi n of x is equal to some constant times sine n pi over a. This is the k, and that's x. So this, I require this to be 1. Then this is from 0 to a dx. Let's take a to be real, right? We can assume it to be real. If there is like an overall complex phase, it doesn't matter. So this is a squared sine squared. Let me write k for short, kx. How do I integrate sine squared? Any suggestions?
1 minus cosine 2x.
Exactly. So this is, if you want the cosines, cosine 2x is equal to cosine squared x minus sine squared x, which is squared, and this is 1 minus 2 sine squared x, then sine squared. Let me now replace x with kx. Sine squared kx is equal to 1 minus cosine kx, divide entire thing by 2. So this, we require this to be 1. And I can take a square outside. What's that? Oh, yes, thank you. Absolutely. This is 2kx. This is 1 over 2 minus 1 over 2 cosine 2kx. And this is going to be a squared 1 over 2 x from 0 to a minus 1 over 2 times 2k, and cosine is, I think, sine kx divided, I think I already divided it, sine 2k x. This is also from 0 to a. And now this one is trivial, right? This is sine 2k a is equal to sine, let me write it a little bit bigger here. So sine 2k a is equal to sine 2 times n pi over a times a. Cancel a's, but I know 2 pi times n is 0, and so is sine 0. So then this term I don't need to worry about. And this second term, so this equation is equal to a squared a over 2, and we require this to be 1 for normalization, then a should be equal to 2 over a. Good. Then the full set of solutions are psi n of x is equal to 2 over a sine n pi over a times x. Here, let me give you a few seconds if you want to do this. I don't know about you, but whenever I feel like, oh, this is like elementary, I can do it, and I skip doing it. And when I really have to do it, it blows up. And I get embarrassed. So I suggest you make sure you can do it, because you never know where you will fail. So it's better to try. So let's sketch the solutions. So this one, something like that. So this one is going to be psi, this one is going to be x, and this is x is equal to a. And let's sketch just a couple of these. And this one. And the first one is n is equal to 1. And it is going to be something like this. And the second one is n is going to be 2, something like that. And the third one is going to be something like that. And so on. The terminology, we call this ground state. Minimum possible energy is a special state. Generally, physical systems, they prefer to be in the minimum possible energy. So this is first excited states, and this is second excited state. You can see also like there are like some symmetry, nice symmetry properties. With respect to center of the box, this one is even. That's generally the case. Ground states are even. So this is odd. With respect to center of the box, this is also even, and so on. It goes like odd, even, odd, even. So this one ground state has no node. This is also generic. Typically, ground states in nature are nodeless. It's actually a theorem due to Feynman. But this one has one node. And this one has, these are the nodes I'm showing you. This is 2 nodes. And how many solutions do we have? Infinite, right? There are like infinitely many solutions. Yes, yes, thank you. Yes, yes, thank you. These are all A's. See like this. Any questions? Yes.
Then these also will oscillate in time as well as.
I will come to that. I will form a time-dependent solution using these solutions, and that most general solution is, yes, going to be oscillating in time if you calculate any observable or density. Yes. Now let me rewrite the normalization. So this is from 0 to A psi n, and in the most general case we call it psi star, but in our case, in the present case, we have a simpler real function, but it doesn't matter. Let me just keep writing psi star, and this is psi n x, and this is 1, and what we call this normalization. So this is the key word. And it would be curious to see what happens if you just change one of them, right? Suppose this one is not n, but m. And we have all of these functions in our hands, and we can try and see how it behaves. And it can teach us something about the quantum mechanics. Let me write and ask if you can do this. This is a little bit trickier, but not too much. From 0 to A. Because of this 2 over A normalization, there's one normalization here, another one here. Let me write it in front. So this is, and they were like square roots. Because of 2 of them are here, I am going to get rid of square root by this. And the first one is going to be sine n pi over, okay, this is m. Let me write it a little nicer. So this is m pi over ax, and the second one is also sine, but this is n. How do I calculate that? So the way I remember is like I Google Wikipedia and I look at cosine, and I use this formula. Cosine u, if you have minus v, okay, let me write it here, it's not going to fit. Cosine u minus v is cosine u cosine v plus sine u sine v. I think you guys probably know this better than me. And the other one is, if this is plus, this one is minus. And you can sum plus and minus and cancel the first term, and you have like sine u and sine v. And that's exactly what you need. Let me write this here. So let me put this here. And what this will give you is 2 over a. And there will be 1 over 2 because of this, because I'm going to sum 2 of these, 1 over 2. And also this is dx from 0 to a dx. Cosine, let me write it like this, cosine m minus n pi over a x, and I need to have minus cosine, exactly the same thing. But with plus here. Okay, let me give you a moment to stare and convince yourself that's the case. Good. And this one I can integrate, right? This is easier to integrate. And the way you integrate is, let me just write one. So this one. The integral of cosine is sine, and you divide the entire thing with the argument. And you put the limits from 0 to a. And when you put a, sine some integer times pi, right? A's are going to cancel, and 0. And sine 0 is 0. So this entire thing is 0. And similarly here, if you take the integral, this is sine, and argument will be in the denominator, and you put from 0 to a, and sine integer pi is 0, sine 0 is 0, and this entire thing is 0. As a result, this entire thing is 0. So that means this curious case, if m is not equal to n, this one, okay, we were wondering what this is. I left it like 1. This one is 0, but this one is 1. And there's like a compact way of writing this. Let's introduce so-called Kronecker delta. I may sometimes call it Dirac delta because they kind of, one is function, this one is series, and this is delta m n is 1 if m is equal to n, and 0 if m is not equal to n. And then this expression can be written, so this object we started wondering about, can be written like delta m n. So the previous one we call this, this one we call normalization. This one is, I will call it orthonormality. So that's some keyword we need to get used to. Any questions? Now I want to remind you, like this high school geometry, you want
Why we are doing this side n and side n?
Let me explain, and then like in 2 minutes later I'll ask you again if that answers your question. Is that okay? Suppose, let's think about this three-dimensional space, and I want to call E1, E2, and E3 like the unit vectors in x, y, and z direction, right? And we know, right, everybody knows a little bit geometry, like if you have E1 dot E2, what is that? The inner product of E1 with this, 0, right? Because of cosine theorem, whatever you use, E1 dot E3 and E2 dot E3, these are all 0, like you said. What about E1 dot E1? This is unit vector, this is 1, E2 dot E2, and this is E3 dot E3. Like it turns out, like these psi m's and psi n's kind of behave like these unit vectors, right? Because if I have to replace inner product with integrals, integral and taking complex conjugation, I define new rules to myself with integral. Then what I have is like this psi n star psi n dx. This is kind of like this object, right? I can map this much simpler operation with this kind of operation. So this is one. And this other one, E1.E2, is going to be exactly the same thing. But n and m are replaced. So this is 0. So they are kind of like orthogonal, right? Does that answer? So they behave like these unit vectors, but the space we are working, I want to remind you, is not simple Euclidean space, right? We are in like some weird space. We are solving differential equations, and we have like Schrodinger equation, and the name of that space is generally called Hilbert space. We'll talk more about, but I think when we have the opportunity now, it's good to give the names and argue the arguments. Any questions? And that's the answer to your question. Good. So if these things behave like unit vectors, what can we use the unit vectors for? We can use unit vector, for example, any three-dimensional vector, let me call it A. I can write it in terms of unit vectors. A1, E1 plus A2, E2 plus A3, E3, right? Give me any vector, you can decompose it. And if I can do this with like this simple space, why not I do the same thing with this complicated space? Like, and the question is, can I do this? Like, give me any function which maps to this vector. Can I write it in terms of these solutions I found? And it's reasonable to anticipate the answer is yes, right? I can do this by choosing a correct set of CNs. I can always do this. And now we have these two expressions. It's easy to find what CNs are. Just take this expression, multiply with psi m star, right? Multiply with psi m star. This is x, this is also x, and integrate dx and integrate dx. But we just calculated what this thing, right? This is, we said this is delta m n. And let's look at this series. Like there's like, this is n is equal to 1 to infinity, Cn delta m n. And this function tells me whenever m is equal to n, this is 1. In all other cases, this is 0. But this immediately tells me that there are all these terms in the series, but only Cm is going to survive. Right? All the others, because of this nice property of Kronecker delta, will be killed. If you want, this is kind of like derivative, and this is kind of like integral. Derivative and integral, they kill each other. Then the appropriate set of Cm's is going to be this dx psi m star of x, f of x. And the name for this is completeness. Solutions form a complete set so that I can express any other function in terms of these functions. Yes? Yes.
Then it means whatever fx is, it can be written in terms of sine and cosines.
Yes. Exactly.
All the cosines and sines.
Yeah, actually, that's like, right, that's called Fourier series. I don't know if you have taken that course, but this is called Fourier series. Right? You can expand any function in terms of sines and cosines.
And it's a new basis.
That's exactly the case. That's exactly the case, right? There's nothing else. Give me any nice function. Nice function means it's square integrable. Square integrable means it's like you can normalizable. Any normalizable function can be written in terms of sines and cosines. And I think mathematicians prove this, right? I think this is something called Dirichlet's theorem. And if you want, you can take something called functional analysis, and you can spend like your entire career to see if that is doable, or what are the edge cases this is not doable. But here, it is reasonable to expect reasonable functions are going to have reasonable behavior like this. Good. So by the way, like we are doing all of these things for particle in a box, infinite potential, but these results are general. Any other potential, give me, they are going to have the same set of solutions. All of these rules, completeness, normalization, orthonormality, they are valid. They are generic results in quantum mechanics. Let me write one more thing, and I know it's a little bit overload, but let's finish the argument so that you can have the entire package to think about. I think it's about your question. Now, if that's the case, I can write stationary states. Let me just first write the summary, stationary states. Now I use uppercase psi n. It's going to be x and t dependent. And there's this 2 over a. There is like sine n pi over a x. And the exponential part is minus I over h bar. Energy is h bar squared over 2m pi squared over a squared n squared times t. Right? These are the stationary state. We solve the problem. And based on what we argued in the previous lecture, the most general solution psi x comma t is going to be infinite sum, n is equal to 1 to infinity. There's like these Cn coefficients, and I have exactly the same function here. Alternatively, like we can turn the problem around. Suppose a reasonable function is given, like let me call it psi x comma 0. As long as it's normalizable, right? As long as you can integrate after taking the square, it is a reasonable function. And you can say, suppose I don't solve the Schrödinger equation, I push this solution in the Schrödinger equation, what is going to happen? And what will happen is this solution is going to behave like this, psi xt. As you let the clocks tick and time evolve, this solution is going to turn into exactly the same thing, like this. And the expansion coefficients, Cn, are going to be determined exactly the same manner. Dx, psi n star of x, and this function. And we all have exercises on this, and we are going to have more to say about this. But at the moment, this is what I want to leave you with. And I want to emphasize one more time, this result is valid for any potential. Box potential makes it easy for us to convince ourselves this is the case. Any questions? Any? Yes?
In that case, that change when you put another variable.
So this Tn is constant, yes. But this set of constants you need to find by taking this integral. Exactly. Last of and the full set is going to determine your evolution. All right. Thank you.